Hello, in this video, I'll walk you through three deep learning models covering the implementation, evaluation matrix, and error analysis and visualizations. The first one, as you can see, is a classification model that I've implemented on a UCI adult income dataset. This model predicts whether a person earns more or less than 50k dollar per year based on features like education, occupation, and age. Since this is a binary classification problem, our goal is to maximize accuracy while ensuring the model isn't biased towards any particular class. Here we have loaded the data set and built the model. For instead of using weights and biases, I've used TensorBoard here, and this is the classification report. Moving on to the metrics, the accuracy tells us how many total predictions were correct. High accuracy is good, but it can be misleading if the classes are imbalanced. The precision score measures how often the model is correct when it predicts high income. If a precision, for example, here is 0.80, then 80% of the time when we predict is greater than 50k. That is actually true. A high precision means fewer false positives. Recall tells us how many actual high income individuals were correctly identified. If the recall is 0.94, it means 94% of all the actual are greater than 50k earners were caught by our model. A high recall is important if missing a positive case is costly. F1 score matters because it measures the balance between precision and recall. As we can see, the F1 is equal to 0.91. It means the model is performing well overall without favoring any over the other. A low F1 score means the model is making trade-offs which should be analyzed further. Looking at the ROC and the PR curve, the ROC curve, that is the receiver operating characteristic, if the area under the curve is equal to 0.91, it means our model is 91% effective at distinguish high versus low income earners. Closer to 1 is better. The PR curve stays high with a good balance. It means the model is making solid trade-offs between precision and recall. And this is the per class analysis. Now let's go ahead and analyze our regression model. Here we are predicting wine's quality score 0 to 10 based on chemical properties. Looking at the key regression metrics, the mean squared error is equal to 0.68. It means that on an average, our predictions are 0.68 points off from the actual quality score. The lower the mean squared error, it is the better. The mean absolute error, it means that on average, our predictions are off by the value of the mean absolute error in either direction. The R squared value is equal to 0.04. It means our model explains the variance in the wine quality. Looking at the scatter plot of predicted versus actual wine quality, we notice that some lower quality wines are being over predicted. This suggests that the model may not be handling low quality wines well, potentially due to the bias in the dataset. Moving forward with the image classification model, here I am using CFAR 10 dataset. This CNN model classifies images into 10 categories: airplane, car, birds, cats, etc. Here I have loaded the dataset, and again I'm using TensorBoard for weights and biases. Looking at the key metrics, the accuracy is around 0.69, which suggests that 69% of the test images were correctly classified. Per class precision and recall. If a dog has precision 0.75 but recall point, it means 75% of the predicted dogs are correct. 90% of the actual dogs were identified correctly. If recall is high but precision is low, the model is over predicting that class. Let's analyze the confusion matrix. From the confusion matrix, we notice that the model often confused cats and dogs. This suggests that these classes share similar features like fur and shape, making them hard to distinguish. And here we can see the misclassified images as well. Now looking at the ROC curves and the PR curve, if the area under the curve for airplanes is 0.95 but for birds is 0.78, it means the model is great at identifying airplanes but struggles with birds, possibly due to the background clutter in the images. Error analysis after the misclassified images show that dogs are sometimes classified as cats due to similar feature. Trucks are confused with cars likely due to similar shapes. This tells us that we might need more data augmentation and larger CNN architecture.